This PowerPoint is about bond polarity, which simply means once a chemical bond is formed between two atoms, is there any degree of charge development that is formed? The type of bond made, we talk often about covalent bonds versus ionic bonds, but the type of bond that's made really lies on a continuum, and on one end of that continuum is a completely nonpolar covalent bond where valence electrons are shared completely equally, and the other extreme is an ionic bond where there's no sharing going on at all. One of the atoms has completely transferred one or more valence electrons to the other atom. So you should get yourself familiar with the definitions at the bottom of the page here. That nonpolar covalent means equal sharing of electrons. A polar covalent bond is still sharing, it's still a covalent bond, but not quite equally. So you get some partial development of charge separation. And finally, of course, an ionic bond is transfer of electrons. And this is just kind of a cool picture demonstrating nonpolar covalent equal sharing versus polar covalent. What determines the type of bond formed is the difference in electronegativity between the two atoms that are bonding. Now be careful here. If you're asked, it's not simply electronegativity that determines the type of bond, it is the difference in electronegativity. So to remind you what electronegativity is, it's one of the properties that shows periodic trend, and it moves from a low electronegativity in the lower left corner to fluorine, which is the highest electronegativity. And just kind of a reminder, the noble gases have zero electronegativity. Electronegativity, of course, is the attraction an atom has for bonding electrons, and since the noble gases already have a full outer shell, they don't tend to want to make a bond, so they don't have any electronegativity. Alrighty, so we have actually come up with ranges. I told you that the type of bond really lies on a continuum, but we've come up with ranges of differences in electronegativity, and we use those ranges to classify a bond. So if a bond has a difference in electronegativity between 0 and 0.4, then we call that a nonpolar covalent bond. If the difference in electronegativity lies between 0.4 and 2, we classify that as a polar covalent bond. And finally, if the difference in electronegativity is greater than 2, that is an ionic bond. All right, so the type of bond that is probably the most common and also can be the trickiest to label and describe is a polar covalent bond. So if you have a polar covalent bond, what does that mean? That means that of the two atoms sharing valence electrons, one of them hogs the bonding electrons more than the other one. So think of it kind of as a tug of war where the more electronegative atom is winning, really. It's pulling the bonding electrons closer to it. And because of that, we have something, we have somewhat of a separation of charge where we talk about the more electronegative atom as having a partial negative charge. And this little weird sign is a partial negative. To me, it looks like a figure 8 where you don't close it, but I think it's actually a little lambda. So that's partial negative charge, and then the less electronegative atom we label as having a partial positive charge. And we can also say another way to talk about that separation of charge that's developed is to say that polar covalent compounds have dipoles. Same thing, separation of charge. And you draw a dipole, you may have seen this in physics, with an arrow. Now the arrow head, the tip, is over the more electronegative atom, and the other end of the arrow, which kind of looks like a plus sign, goes next to the less electronegative atom. All right, so this is kind of a visual, what I was talking about. There's not like real distinct breakouts. Okay, this is nonpolar covalent, this is polar covalent, and this is ionic. It really is a continuum, and the breakoff points where we call it a different type of bond are somewhat arbitrary. So you may run across a text that says, for example, everything 1.8 and above in difference in electronegativity is ionic. So just be aware of that. All right, so let's talk about examples of the different types of bonds. Nonpolar covalent bonds. They share equally, and remember the range. That means the difference in electronegativity in order to be a nonpolar covalent has to be very small. So the two atoms bonding have to have very similar electronegativities. So some of the most obvious nonpolar bonds are the diatomic elements. Obviously, since there are two of the same element, the electronegativity for the two atoms are identical, and therefore the difference in electronegativity for diatomics is 0. So the diatomics clearly are nonpolar. They share totally equally. One other type of nonpolar, common type of nonpolar bond that you're simply going to have to memorize is the carbon-hydrogen bond. I'm going to show you a table of electronegativities in a bit, but you'll see once you look at that table, I think the electronegativity for carbon is 2.5, and I believe the electronegativity for hydrogen is 2.1. So the difference in electronegativity for a carbon-hydrogen bond is around 0.4, which still puts it in the range of a nonpolar covalent. And that'll be important later on explaining properties of certain molecules. All right, so here's a table of electronegativities. The element with the highest electronegativity is fluorine, which is arbitrarily given a value of 4. And of course, remember the noble gases have 0 electronegativity, but other than that, the lowest electronegativity is cesium in the lower left corner. And so you may be asked to classify certain bonds, and in order to do that, you're going to have to calculate the difference in electronegativity. You'd have to be given a table of values like this. All right, back to polar covalent bonds. It looks like some of my symbols did not import very well into this lecture, so I think that was a partial sign. Yeah, okay. Another example of a polar covalent, hydrochloric acid. And if you were to calculate the difference in electronegativity, you would confirm that it's in fact polar covalent. And I will likely then ask you to either draw the dipole for that molecule or label it with partial charges. So if you chose to label it with partial charges, you just make sure to put the partial negative charge over the more electronegative element and the partial positive over the less electronegative. Or if you use a dipole arrow, make sure the tip of the arrow lines up with the more electronegative atom, and the plus N lines up with the less electronegative atom. You will read some problems. Instead of saying that a certain molecule is polar, it may give you dipole moments of various molecules. So I don't tend to use that vocabulary, but I have seen it on the final exam, the ACS final. So dipole moment, the larger the dipole moment, the more polar the molecule. Okay, so that's really all you need to know. You're not going to have to do calculations with it. So, of course, since a diatomic is completely nonpolar, there's no difference in electronegativity of the two atoms bonding. Therefore, the dipole moment is 0, meaning it is not polar at all. Okay? And so be able to look at dipole moment values and order substances from least polar to most polar. We can see here that lithium fluoride is the most polar of these three given, which is not a surprise since that's the only ionic compound. We know ionic compounds are the most polar of all. All right, so, there we go. So the polarity of chlorine's 3, that of hydrogen is 2.1, so the difference in electronegativity between HCl is 0.9, which puts it in the polar covalent group. Alrighty, here are some for you to try, and there are some in the Chapter 9 homework also. We just did hydrochloric acid, so let's do sodium chloride. I will warn you that there are some ionic compounds that when you calculate the difference in electronegativity will actually put them into the polar covalent group instead of ionic. So I hope I didn't leave anything like that in homework, but if I did, don't worry about it. All right, sodium chloride. So chlorine has electronegativity of 3, and sodium has an electronegativity of 0.9. And so the difference in electronegativity for sodium chloride is 2.1. Yes, so that does correctly classify it as ionic. Carbon tetrachloride. Now, this one, I want to point out to you, you're only looking at 2 atoms at a time. You're only looking at a single bond. So don't pay any attention to how many of each atom there is, and don't multiply electronegativity by anything. So we're just looking at 1 carbon chlorine bond now. So chlorine has an electronegativity that we just found out of 3. Carbon has an electronegativity of 2.5. So the difference in electronegativity with a carbon chlorine bond is 0.5, and that just barely puts it into the polar covalent category. Finally, ammonia, NH3, that's a common name, ammonia. So let's see, nitrogen also has electronegativity of 3, and hydrogen 2.1. So the difference in electronegativity between a nitrogen and a hydrogen is 0.9, and that, of course, is polar covalent. Why do we care about bond polarity? The polarity of a bond, and more importantly, the polarity of an entire molecule, determines all sorts of properties. It determines how it's going to, what other molecules it'll interact with, like what it's soluble in, what it isn't soluble in, what it's attracted to and spends time around, how reactive it is. You will learn later in chemistry that polarity is actually one of the most important properties, because if you have a polar molecule that is some separation of charge, it's going to align with other molecules in a certain way. We know opposite charges attract, right? So if you have a polar molecule, you can see that it's going to align head to tail, so that the opposite charges are by each other. And that particular alignment or intermolecular attraction is going to affect a ton of properties. So on the last slide, okay, so I will leave you with this thought about some of the properties that are affected by intermolecular, intermolecular attraction. Look at all these properties that determines the temperature at which phases change, vapor pressure, how soluble it is in certain solvents, and surface tension, among others, actually. So that's it for this PowerPoint.